Okay, so anyway, review questions 13 and 14. I'm not going to do 13 and 14. I'm going to make something up similar to 13 and 14. All right, here we go. I'm going to draw. Oh, by the way, the thing I'm drawing and doing with you is not even a possibility in mathematics. It's for example purposes only. All right, really driving home this idea for you guys. We good?
Yes.
Actually, you know what? I made an executive decision. I won't even use numbers. That way, it doesn't matter that what I'm doing is not a possibility in mathematics. So I'm going to draw a curve. In fact, I'm going to draw a curve rather similar to one that you have on the review, 13 and 14. I'm going to draw something very similar to that. You cool with that? Great. Here we go. Here we go. We've got a cubic. And I'm telling you, here's some cubic f of x. And now I'm going to put some points on here that are important to us. Those points will be point A, point B. I'm feeling a point, I don't know. This feels like a point C. Here's a point D. Here's a point E. And lastly, point F. So I got a whole bunch of letters on here, okay? Let's talk about f of x by itself. Where is f of x positive? Well, f of x is positive everywhere it's above the x-axis, right? So that would be to the left of A, then from D to F. Remember, we don't use brackets on positive, negative. Where is f of x negative? Well, it's going to be negative from A to D, and once again after F. Okay, so that one's, everybody's pretty good at that. Where is f of x increasing? Well, increasing is going to be when the roller coaster car is headed up. So it starts increasing at B, and I am going to put a bracket at B because it's a change point, and it stops decreasing at E. And once again, bracket because change point, and f of x decreasing to the left of B, but B is a change point, and decreasing again after E, but E is a change point. Okay. And I feel like we're pretty good at those four concepts right there. I could also ask you concave up and concave down on this picture based on where I put it, which letter it represents an inflection point. Just shout it out if you know. Which letter represents an inflection point of this curve?
C.
C. So C would be representing my inflection point. I'm saying it's occurred somewhere around here. And that's a total guess. All we know is that it's between a minimum and a maximum. Cool with that idea? Great. Now, that's like question 12. Question 13 says, what if this is actually representing the first differences of some other function? We'll say that f of x is the first differences of some unknown p of x. Oh, I wrote it too low. You can't see it on the camera. Here, I'll just write it up higher. Some unknown p of x. When you say it's the first differences, what are we actually describing? When I say the first differences of something, what's a word for that? Rate of change, also known as slope. So when I tell you that this thing is representing the first differences of this, what I'm saying is this thing's y values are actually slope values of this. For example, at this unknown point right here where I'm pointing, if this is a positive y value of f of x, correct? But if f of x represents the first differences, this point that is a positive y value for f of x represents a positive first difference for p of x. And when you have positive first differences, what do you know about a curve? What does first differences tell us? Concavity, second differences. Increasing, decreasing. So if I say to you, where is this increasing? P of x is increasing. Again, this is if f of x is slopes. I'm saying slopes instead of first differences. But if f of x represents first differences of p of x, then p of x is increasing everywhere where this thing had positive values. And it had positive values here. But I am going to change it to this. But why did they become brackets instead of parentheses? Because now we're talking about rates of change. And when you change between increasing and decreasing, you get brackets. Yes? If you'd put parentheses here, it's technically a wrong answer, but I would give you partial credit. Because at least you understood what was happening. It's just that when you change between increasing and decreasing, you're going to get brackets. But I'm going to be real with you, a question like this would be multiple choice. And there wouldn't be an option that had brackets and one that was missing brackets, because that's just plain mean. There'd be no reason to do that to somebody. Yes? Because it's here. When you're saying negative infinity, this is an x value, not a y value. Why is an unknown polynomial increasing from d to f? Because this is not p of x. These are p of x's rates of change. So everywhere from here to here, p of x has positive rates of change. If we're talking about the blue one, this is where f of x is positive. This is where f of x is positive. But when is a graph increasing?
When it's going, when the y values are positive.
No, that's where it's positive. A graph is increasing. Hey, a graph is increasing when the rate of change is positive. So if I told you, that this picture is actually a bunch of rates of change, not y values, they're rates of change, then everywhere from here to here is representing positive rates of change of something else.
Okay. And this is literally just like a hypothetical that you're thinking of here?
This is how you do numbers 12, 13, and 14.
But does it, in the question, on 12, 13, and 14, does it say that this is...
Yes. It says exactly what I'm telling you right now.
Okay.
So when would our unknown p of x be decreasing? Our unknown p of x would be decreasing if it had negative rates of change, correct? But if the blue curve represents the rates of change of p of x, then the negative rates of change are when the blue curve has negative values. And that would be from a to d and from f to infinity. But once again, because they are now increasing, decreasing changes, we'll put brackets on them. So what we're having to do is we're having to separate the idea of y values from rates of change values. Okay? Where would p of x have inflection points, I think is the next question. Okay, here's the real question. How do you recognize an inflection point of any curve? Going from increasing to decreasing is a turning point. So let's look at f of x. Decreasing to increasing, turning point. Increasing to decreasing, turning point. How do we recognize an inflection point though? Concavity changes. But what gives us concavity? David? The rate of change changing is turning points. See, here's rate of change negative, here's rate of change positive. What gives us concavity? It's not rates of change. What is it? Yeah. The second difference, the rate of change of the rate of change. If the rate of change of the rate of change is positive, concave up. If the rate of change of the rate of change is negative, concave down. So inflection points happen when the rate of change of the rate of change swaps symbols. If the rate of change of the rate of change, if the second difference goes from a negative value to a positive value, inflection point. If the second difference goes from a positive value to a negative value, inflection point. So if this represents the first differences, then its first differences are second differences of P of X. Its rates of change. If this represents rates of change, its rates of change are the second differences. See, it takes it down a degree, basically. So the rate of change here is negative. The rate of change here is positive. So if the rate of change of the rate of change switches symbol, concavity changes. So if this represents first differences, then B is an inflection point of P of X, because it's where the rates change from negative to positive. And if f of x is the first differences, if f of x is the rates of f of x, then the rate of the rates, it goes from positive to negative here, that makes E an inflection point of P of X. Yes?
So the inflection point for the minimum and the maximum?
Okay. The inflection points of this unknown function, if this represents the first differences, are this thing's turning points. But turning points of a function are never an inflection point of the function. It doesn't work that way. But if this is the rates of something else, then when its rate changes, you're talking about the rate of the rate. That's an inflection point of an unknown function. This is what AP is about. Yes?
Just to check my understanding, is like an inflection point for f of x?
An inflection point of f of x is point C, yes. But if f of x is the rates of change of P of x, then P of x has two inflection points. Here, because this thing changed from decreasing to increasing, and here, because rates changed from increasing to decreasing. Okay? And, yes, Ellie? The first difference of a function tells us increasing, decreasing. When that changes symbol, turning point. The second differences of a function represent concavity. When second differences are positive, concave up. When second differences are negative, concave down. So if second difference changes symbol, inflection point. For example, for f of x, this is an inflection point because the rate of the rate is positive here, and the rate of the rate is negative here. So concavity changes right here. However, if this thing's y values are actually rates of change, then here I have positive rates of change what just happened to me? Oh yeah. When does the rate of the rate change? There we go. This thing's rate is negative all the way to here. So what we're saying is the rate of the rate is negative, and the rate here is positive. So we're saying the rate of the rate is positive. So rate of the rate is negative, rate of the rate is positive for this. That would mean the change happened here. This is an inflection point of an original function that you can't see. Okay? Yes?
So on
This is supposed to be a 6-minute video.
on this specific graph,
On this one that I've drawn here, this specific,
the inflection points of P of x
the inflection points of P of x
are the minimums and maximums.
are the turning points of the rate function, which is f of x. Yes. But if you're just trying to memorize that pattern, he's not listening to me. If you're trying to memorize that pattern, you're going to be upset when you see the test. We don't memorize those kinds of patterns. We understand why the pattern is true. If the rate of the rate changes symbol, inflection point. If this thing's y values are rates, and here it was decreasing, which is a rate, and then here it's increasing, which is a rate. The rate of the rate changed right there. Now, that was all for 13. Now 14 says, think about, and I'll swap colors to orange. Think about the first differences of this. So now this is our function. All this nightmare is gone for you, okay? Now think about this thing's first differences. At what letter does this thing's first differences change symbol for the first time? No. B. First differences is rates of change. Look at all of this is negative rates of change. Here's positive rates of change. Here's negative rates of change. How many times does this thing's rate of change equal 0? 2. Here and here. So if you were going to plot its rate of change, you just said it had 2 zeros, correct? What kind of things have 2 zeros? What degree polynomial has 2 zeros?
2.
A second degree polynomial. So this thing's rate function would be degree 2, a quadratic. So then what degree would this one have been if this was its rates? This is third. What would this thing's been? Fourth. Every time you go up, it adds a degree. And every time you come down, it takes away a degree. So P of x would have been a fourth degree polynomial. Its rate of change function is a third degree polynomial. The second rate of change, or the rate of the rate, would have been a second degree polynomial. Okay? So this thing's rate function would have been a quadratic. In fact, it would have been a negative quadratic because this is a negative cubic. That's how you do 13 and 14. We're going to call it there because it's already way too long.